Hello everybody, my name is Professor Soborno Bari from Bari Science Lab, and today I'm going to take you to Copenhagen, Denmark in 1820, where Hans Oersted had just made his greatest discovery. He just discovered that a current carrying wire can create a magnetic field surrounding it. So to recreate his discovery, we need a wire and current. We have the wires, but is there any magnetic field surrounding them? No. Why? Because there's no current. He observed that you need current to create a magnetic field. So, let's put it in the DC terminal. And then, remember DC is direct flow. And then you have 6 volts, the highest thing possible. And ta-da! But the light bulb, everybody knows that. We're not here for that. We're here for the magnetic field surrounding these wires. First, we have to understand, what is the equation of the strength of the magnetic field? Well, that can be shown right over here. B, remember with an arrow on top of it, because it's a vector, is equal to I mu, so I assume it's written like this. Mu is a constant over 2 pi, the radius of the thing. The radius of the magnetic field, to be specific. Let's find the direction of our magnetic field. For that, we can use the right-hand rule. Let's say we have this wire, this one. Now, let's just re-plug it in for our sake. And now, which way is the current going? It's this way. So take your right hand, use your left hand to just straighten up the wire. Take your right hand, take the thumb, and point it in the direction of the current, which is up in this case. And then move your other fingers to curl around the wire, so they could grab it, kind of like this. Now from that, you can tell the direction of our magnetic field. It's going, if you drew this on a 2-dimensional paper, then it would be going inside the page and inside the table. Now, let's say that this magnetic field, the center is at the 10 centimeter mark, meaning that the radius of this whole thing is 10 centimeters. We need our wire, then we know that the current is traveling up this wire, and now the wire is creating a magnetic field since the current is sparking. So now, let's say we have 10 centimeters from our thing, so 10 centimeters, and then we have another 10 centimeters, or instead this time 20 centimeters for our thing. So let's draw that over here, and then let's call this one A and this one B. And now we want to find what is the current of A, and what is the magnitude of the magnetic field of A, and what is the magnitude of the magnetic field at B. That's what we want to find over here. So we need to use the equation that we erased before. What was that? Well, it was B, not that point. We instead want the magnetic field thing B, which is a vector, you can tell by this arrow. And then you have I mu, kind of hard to draw, then 2 pi r. That is our equation, and now let's plug everything in. First, let's define I to be 15 amps for both ones. Both ones, why? Well, because the the wire can only have one single current value. So it's going to be 15 amps for this problem. So it's going to be 15. Mu is a universal constant, no need to worry. So 15 times 4 times 10 to the negative 7, for pi, and then 2 pi r. So now let's cancel out the bad thing, the things that we do not want. Remember, this is for point A, not point B. So the bad thing that we do not want is pi, since pi is irrational. Now let's cancel out the good things that we also don't want. 2 goes into 4 2 times, and then we have r, which will plug in as 0.1, because if you convert 10 centimeters to meters, then you get 0.1 meters. So now that goes into 150 times. So you get 150 times, we have 2 times 10 to the negative 7th, and then we have 300 times 10 to the negative 7, so we go down 2 ranks, and we get 3 times 10 to the negative 5th power. And now we have calculated it for A. So let's go back and let's take it. A, check. A is equal to 3 times 10 to the negative 5th. Alright, now let's look at B. Since A had this radius, since B has twice the radius of A, that means that B will probably be less far away, so it's going to be more far away, so there's less magnetic field, so there's less power on the magnetic field. So if we do it directly, then we'll see that this is half of what it used to be. Actually, it's double what it used to be. So that means since it's directly related, we can assume that this will halve since the value of the entire thing halved. So we can say it went from something over 0.1 to the same thing, but on 0.2, which means that the value halved because this got greater. So now, since the value halved, we take this, we chop it in half like we have a knife, and then we get 1.5 times 10 to the negative 5th power. See? Completely. Speed running and Orsted's equation. Alright, we'll see you on the next one. Bye.
Bari Science Lab to fall in love with math and science, especially programming.